We found in the previous two examples unique solutions to the systems that we were presented with. In those cases, 3x3 systems had unique x, y, and z that satisfied the equations. But that's not guaranteed to be the case. What we want to know is up front, are we going to have a unique solution that satisfies our equations? And to do that, we need to test for linear independence. And if our system of equations are linearly independent, we will have a unique solution. So the rule is we don't need just the same number of equations as unknowns, but more specifically, we need the same number of linearly independent equations as unknowns. And we have ways of testing this linear independent. More formally, linearly independent means we can't take any combination of our equations and get one of the equations back. And we'll see numerically what this looks like in a little bit in the examples. But we can't take a linear combination of equations to get a third equation, is the basic idea of what we're looking at. So there's some properties of this A matrix that are going to guarantee linear independence of our systems. So the first rule, and we've seen this before, in order to satisfy this, is A must be square. It must have the same number of columns as it has rows. So in Matlab, if we were wanting to automate something to make sure that we're going to get a unique solution, we can take the size of A and make sure that the two values we get match each other. If it's not a square matrix, then we certainly are not going to have a linearly independent set of equations. And the other rule is that A cannot be a singular matrix. What does that mean? Well, A is singular if its determinant is 0. Again, if you haven't had linear algebra yet, don't worry too much about this. We're really just going to look at the test here. If it's singular, that means that it's not invertible. We cannot take its inverse. It's going to be undefined. So a quick way of testing is something invertible is seeing is its determinant 0. Or if we tried to take its inverse, it would be undefined. Either way. Now in MATLAB, either we're going to find that the determinant is 0, or it's going to be a very, very small number due to some rounding errors. And another test we can do is we can find the condition number of A, which is another technique we can use, and make sure it's finite. Now again, in MATLAB, it won't actually necessarily give us an infinite value, but if we get a very, very large number for its condition number, that is telling us that A is a singular matrix, and therefore we don't have a set of linearly independent equations. So let's go back to ones we know are linearly independent, the previous two examples, and just test some of these features to see that it is satisfied that it is not singular and they are square. Going back to example 1, so remember we got this value of x that was unique. We got the same answer all these different ways. So what we can do is we can look back at that A matrix and see that it does satisfy these requirements. When we find the size of A, we see it has 3 rows by 3 columns, which we knew beforehand, but we know that A is a square matrix. And if we find the determinant of A, we find it's non-zero. We get 7. And again, if we take the inverse, we know that it is defined, meaning that A is invertible as a non-zero determinant. And if we look at the condition number of A, we're going to find that it's a finite number. Right, so 5.08, and we'll see what happens if it has a very large condition number, which again is going to imply that it is a singular matrix, and therefore will not give us a unique solution. Alright, so let's then look at the ones we had in example 2. Just to verify, we get the same types of results here. So for this matrix A, again, it's square. We get 3 by 3 as our result. If I take the determinant of A, I get -6, which is not equal to 0, and it's not a small number. And if I find the condition number of this A, I get 47.1. Again, a finite number, and it's not a very large number that we'll see in a case where we don't have linear independence.